We've learned in the past about Lewis structures, shapes, and polarity, how they influence the intermolecular forces, which affects melting point, boiling point, solubility. And then hopefully we'll have time to do entropy. Entropy is not a molecular property, so I've made it a different color. Okay, quickly revision. The electronegativity increases across. You do need to know these trends when you're trying to work out the dipoles. And of course, electronegativity increases up a group. Now, fluorine landed up in a slightly wrong space there. It should, of course, be up there. Whoops. Okay, and of course, why you need the electronegativity is when you've got two atoms bonded to each other. So here's oxygen and fluorine. The fluorine is the more electronegative, and so there's going to be a difference in electronegativity. And as we go across the periodic table towards the left, so from oxygen to boron, you can see the difference is getting bigger and bigger until it is ionic. So that's why you need to know about electronegativity. And remember, it's a property of an atom or an element. It's not a property of a molecule. So just make sure you use that term correctly. Every year the examiners say something about students not using this term correctly. Right, so quick revision. To work out the polarity, you need, of course, the Lewis structure first. So if we did ClF3, Cl, group 17, 7 electrons, fluorine, also 17, so 7 electrons. So we have 28 valence electrons in total. Why 28, Andrew? Okay, I see you're typing anyway. But why would we have 28? Where the 4 come from? Okay, you're really getting ahead. That's great. Okay, the 4 is from the chlorine plus the 3 fluorines. Okay, so we can draw this molecule. Now that we have the Lewis structure, we go into the next step, which is electron geometry. And remember, what we have to do here is count the number of regions of negative charge. So this bond is 1, this bond is the next one, 2, this bond 3, 4 for that pair, 5 for the next pair. So if we have 5 regions of electron density, what is the shape? So there are those 5 basic shapes, remember: linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, and octahedral. So which one is for 5 regions of electron density? The bipyramidal, correct. So once you've worked up that one, and of course you've got to say the trigonal, then we can go into the molecular shape. And now we say, right, we've got 5 regions of electron density, but of those 5, we've only got 3 bonding pairs of electrons and 2 non-bonding pairs of electrons. Again, in exams, make sure you say pairs of electrons. Just don't say just bonding pairs and non-bonding pairs. You have to show, you know, you're talking about electrons. And if you learn your shapes, you'll know that is the T shape. And now we have to look at the electronegativity and bond dipoles. So the chlorine in the middle is more or less electronegative than fluorine? Less. So there's going to be a bond dipole towards each of the fluorine atoms, leaving this slightly positive and this area slightly negative. Is this molecule symmetrical? You're not sure? Okay, it actually isn't, and the best way to check is, I know if you cut it in half and then you cut it in half, but actually the way you check it is you have to go along each bond. So if I cut it in half along here or along this bond, this side is not the same as that side. So it's actually not symmetrical. If I go along this bond over here, yes, that side is equal to that side, but it's got to be symmetrical in all the planes, not just one. So that's just to talk about the electronegativity. So we've got polar bonds, and you can see that where the chlorine is, it's more positive, and where the fluorine is, it's more negative. And the bond dipoles don't cancel. don't say bonds cancel, or don't cancel, bond dipoles don't cancel, because that molecule is asymmetrical. As you say, if you cut it across any bond, all the planes must be the same. So here's now this example of last time, and you were trying to tell me last time where I went wrong and I just didn't see it. So I thought I'd just do it again here. So the perchlorate ion, it's ClO4, so there is the Lewis structure, which was correct. And those are the valence electrons, because it's 1 chlorine, 7 plus 4 times 6 electrons for each oxygen, plus 1 electron for the negative charge. And once we've drawn that structure, we look at the number of regions of negative charge to get the electron geometry. So 1, 2, 3, 4. Remember, every double bond is a single region of negative charge. And if it's 4 regions of negative charge, what will be the shape? Remember, the basic shapes are linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, and octahedral. So I know you're typing there. Tetrahedral, correct. And now we look at the molecular shape. How many bonding pairs, how many non-bonding pairs? Well, they are all bonding, and if they're all bonding, it's the same as the basic shape. So it'll be tetrahedral. Now we look at the electronegativity. Oxygen is more electronegative than the chlorine, so there'll be a bond dipole towards each of the oxygens. So this will have a negative area around it, and each bond is polar because there's uneven sharing. But as you can see also from last time, we saw it's red all on the surface because it's negative, being a negative ion, but that negative charge is distributed equally, so the ion is actually non-polar. Okay, it's a non-polar negative ion. Any questions so far? That's revision from the previous 2 lessons. No. Okay, so now we go to the forces of attraction. And the first one is the temporary dipole forces of attraction. There are 3 you have to learn. So this is the first one. It's got lots of other names. If you look at YouTube or look at the web, it's also called instantaneous dipole. And that's because this force of attraction is caused by, as you've got a molecule, those electrons are not stationary. Yes, it's fleeting. Those electrons are moving all the time, and they're not all moving in sync like a beautifully ordered cars on the motorway. As you know, from the motorway, there's cars speeding, there's cars going slow, there's, it becomes, there's a traffic jam, and then it clears up. So you can imagine this like being cars on the motorway with traffic jams here and there, and others are free-flowing. And where the traffic jam is, there are lots of electrons, and so it's slightly negative over there. But then, as you know, with traffic jams, they disappear, and perhaps another one forms later down the track. So it's constantly changing. Now, they're also called instantaneous or fleeting, or London forces, dispersion forces. London and van der Waal were 2 chemists that were working with this, so that's why their name has been put to it. It's found in all molecules. So it doesn't matter if it's water, like a polar molecule like water, or a non-polar molecule like carbon dioxide. All molecules have electrons moving around, so all molecules will have temporary dipole forces of attraction. Now, the strength of this intermolecular force, it's normally weak, but it can be influenced by 3 things. The mass of the molecule. So if I was looking only at mass, so I was looking at 2 isotopes like water and D2O, which is the heavy water. Heavy water is made out of the isotopic deuterium oxide, and that has a heavier nucleus. You'll find D2O has got stronger forces of attraction than water, H2O, and that's simply because of the heavier nucleus. If I was just simply looking at bigger molecules, so one was 20 grams per mole, the other one was 40 grams per mole, okay, it's not just the nuclei perhaps changing, but also the number of electrons. So the number of electrons also has an effect. The more electrons, like some more cars on the motorway, there can be more traffic jams, so more bunches of things, so it's going to have a stronger attraction. So I've tried to show it's a weak attraction with a lower mass and a stronger attraction with a bigger mass, more molecules. The shape of the molecule also affects it. So if I've got 40 and 40 in terms of its mass, but one molecule is long and thin and the other one is round, yes, each attraction is perhaps the same based on its mass and number of electrons, but those round ones can't get as close to each other. So compare those two with long, thin molecules. They can pack more closely, so each one might be the same strength, but because there's more of them, it means I've got to break more of those forces of attraction if I want to do anything with them. So overall, I'm going to need more energy. Overall, there's going to be a stronger attraction, just from more numbers. And as I say, they tend to be weak. But you can end up with much heavier molecules. Tar, for instance, tar is pretty much a solid at room temperature. Candle wax as well. Those are all non-polar molecules though, but they have really, really strong force of attraction because they're so big and heavy, the molecules. Now I'm going to go to this flash diagram over here, and that's what you saw earlier. So what I'm trying to show in this diagram, I have got non-polar forces, non-polar molecules, sorry, but the electrons are constantly moving. So where it suddenly goes red, it's where there are more electrons, and where it goes blue, it's when there are less electrons. And those green dotted lines are showing the attractions. They're very fleeting. They form and gone, form and gone, form and gone. If I freeze the time, you'll notice sort of here, most of the electrons have gone to this side, leaving that quite positive, which is influencing this. So it's the more positive end has been dragging the electrons of this molecule over to attract it. Here we've had this one attracting that one, so we've got two negatives together, two positives together there. But can you see how they're influencing each other? At the moment, that one's completely white, so it's the electrons at this point in time is equally distributed. If I go make it move again and I stop, you can see it's changed. So very fleeting non-polar attractions and non-polar molecules. What I've got down here, I'm trying to show polar molecules. Now these polar molecules must have a permanent molecular dipole. So if they've got yes, and there'll be stronger attractions, because can you see, look at the color of that negative or even that negative compared to this. There's going to be like a stronger magnet, a more negative end and a more positive end compared to the non-polar molecules. So it's a permanent dipole, so we're going to get these permanent attractions. So these never vary. They're going to stack up where the negative end is always next to the positive end. But do you notice that the shading isn't exactly 100%? This red isn't quite as deep a red as this one down here in the bottom left, or even the one in the top right. And the reason is, when I go back to the instantaneous view, remember I said the temporary dipole force of attraction occur in all molecules, even polar ones. So if I carry on over here, can you see the left-hand side is always blue for the top row, and the right-hand side is always red for the top row. But I also have my electrons whizzing around. So because my electrons are also whizzing around, sometimes that negative charge is even more negative, and sometimes it's less negative. So it's constantly changing. So we've got these permanent attractions, and we've got these temporary ones whizzing around as well. So here we've only got one type of force in the non-polar molecule. In the polar molecules, we've got two types of forces, the temporary and the permanent dipole forces of attraction. Any questions so far? No. Okay. Right. So what we're going to carry on with now. There. Okay. So we've had a look at this. So I'm just going to flick through. Now we're going to the permanent dipole force of attraction. They're also part of that van der Waals. Both temporary and permanent are van der Waals. And as I say, they're found in polar molecules, and the only thing that changes the strength of that attraction is the size of the molecular dipole. So the stronger the permanent dipole or the molecular dipole, or the higher it is, the stronger this type of attraction. So here I've tried to show this is not particularly negative, that is not particularly positive, so it's a weak molecular dipole, so not a very strong attraction between them. But if I have a molecule with a big molecular dipole, so it's fairly negative and fairly positive, then I'm going to have a much stronger attraction between them. Okay, and as I say, they're normally stronger than the temporary dipole because they're there all the time. But remember the factors that influence the temporary dipole. If you have heavy, big molecules, lots of electrons, you can get very surprisingly strong intermolecular forces of the temporary type. So what I'm trying to show here, CCl4, is that a polar molecule or a non-polar molecule? Non-polar, correct, because those chlorines are symmetrically arranged around the carbon. CHCl3, is that a polar or a non-polar molecule? Yeah, correct, Andrew. This, because of symmetry, is a non-polar. CHCl3, is that polar or non-polar? Polar. But look at the boiling points. The boiling point for carbon tetrachloride is much higher than the boiling point for CHCl3. Now, if you think of what is boiling point, and I'll also discuss this later, but it's really you putting an energy to break these forces of attraction, because when you boil, I have to pull those electrons, pull those molecules apart, which means I've got to break every single one of these attractions. So the stronger the attraction, the more energy. Now, because this one's polar, you can't just say, oh, because it's polar, it's going to have stronger forces of attraction. You have to look at the temporary dipoles as well. And because of its big mass for carbon tetrachloride, 154 grams per mole compared to only 1/3 the size, 50 for chloromethane, it's going to have very strong temporary dipole forces of attraction. If I go for something down here, here's one where they're fairly similar in molecular mass or molar mass, 44 compared to 48, although that's still higher. Propane is non-polar, and fluoroethane is polar, and it's got a slightly higher boiling point. -37 is actually higher than -42. I know the number looks smaller, but remember we're going along the negative, number line, going towards a positive, and so that's higher. I hope that's clear. Yes. So Andrew, what you correct? A big molecular mass will lead to this much stronger temporary dipoles, so it'll have an overall bigger or higher boiling point. Right. The final one is the extreme end of the permanent dipole force of attraction. So when you have something that is so polar, the molecular dipole is so big, but it's not quite ionic yet, we get this case of hydrogen bonding. Now, it'll only happen in specific circumstances, and you've got to be really particular in how you write this, because to have hydrogen bonds, the molecule must have a hydrogen atom covalently bonded to a nitrogen, an oxygen, or a fluorine. Why those three? Why not sulfur or phosphorus or so on? What's special about nitrogen, oxygen, and fluorine? They've got a very high electronegativity, and they're also small molecules. Chlorine, and I was looking actually at a German YouTube clip, and they put chlorine in here as well, but we don't regard it. Chlorine is quite close to oxygen, or actually very similar to nitrogen. I think they're nearly identical in terms of electronegativity. But yeah, because nitrogen is so small compared to, say, chlorine, it's not so much shielding, it's in terms of the number of valence shells of electrons. The hydrogen gets closer to the nucleus for nitrogen than to chlorine, so that nitrogen atom can strip the bonding electrons from hydrogen more strongly than chlorine can, simply because although they might have the same attracting strength, it's like having two magnets of the same strength, but if I hold the other magnet further away, it's not going to feel the strength as much as if it is closer. So these are all very small atoms and very electronegative. The next layer down of sulfur, phosphorus, chlorine are bigger, so it can't attract those bonding electrons from the hydrogen as much. So you have to identify that there has to be a hydrogen covalently bonded to one of these atoms. The actual hydrogen bond is from the hydrogen of one molecule to the oxygen or nitrogen or fluorine of another molecule. And I think the easiest way is to simply draw it, because if you draw the thing, then you know immediately what's covalent and what's the actual hydrogen bond. Most students will write something like, the hydrogen bond is formed between the hydrogen and the oxygen. And that's where they leave it. Can you see that's too vague? Because you're working out, is it the hydrogen covalently bonded towards the oxygen? Are they talking about the hydrogen to an oxygen in the same molecule or in a different? So draw the structure, highlight that hydrogen bond, and it's a picture paints 1,000 words. And as I say, it's normally the strongest. But again, remember, your temporary dipole force of attraction can even be stronger than this. If I have a really big molecule, even if it's non-polar, it can have a higher boiling point. Right, and then with solubility, we'll go into this when we do solubility. Actually, I'll just leave this now. I'll do it when we do the solubility. It's really just to say, if I have water, I can dissolve something that doesn't form hydrogen bonds in itself, but because it has an oxygen, it can form a hydrogen bond with the hydrogen of the water. Okay, right, so let's go very quickly through this. BRF3, what sort of intermolecular forces are found? Now think of all three types. Okay, now that is not going to get you anywhere for level 3, Andrew, because you have to be specific. At level 2 that was fine, but not level 3. So you have to say temporary dipole forces of attraction and permanent dipole forces of attraction, because the BF3 is a polar molecule. And the only way you're going to know that BF3 is a polar molecule is if you draw the Lewis structure, work out the electron geometry, work out the molecular geometry, and then do the polarity. So do all those steps. Methane, non-polar, so it'll only have one type. CF4, what do you think that will have? Okay, CF4 is actually non-polar because the fluorine is distributed around. I mean, I'm dumping this on you and you haven't had time to draw the Lewis structure and so on. Obviously in the exam and in the booklets you will be drawing this to work it out. So I'll perhaps just go through it. If you're watching the recording, see if you can work it out before you see the answers. And ozone, remember last time we saw was polar, So it has both types. And here you have a hydrogen attached to an electronegative oxygen. So it's going to have 3 types. So you must list all 3. It's always got temporary dipole forces of attraction. It is polar, so we'll have permanent dipole forces of attraction. And it has a hydrogen attached to the electronegative, or covalently bonded to the electronegative oxygen. So it will also form hydrogen bonds between the molecules. Right, so how do we use this to explain boiling points? Now, invariably somewhere along the line you have to show you know what a boiling point is. Most students will say, oh, it's when liquid changes to a gas. That gets 0. You have to say it's the temperature at which a substance changes from a liquid to a gas. So it's a measured point, it's the temperature. So it will be in degrees centigrade. And as I said before earlier, you've got to break those intermolecular forces to separate the molecules, because what's happening when it changes from solid to from liquid to gas, separating the particles. So the difference between melting point and boiling point is melting, I only have to separate some of the molecules or break some of those forces of attraction, because in a liquid those particles are still really close together, so you don't have to break them all. With a gas, they separated from each other, so I have to break pretty much all of them. Okay, you could even say all. I noticed last year's exam paper wanted you to say all. So if I have this, here is a point of methane, boiling point minus 164, CF4, non-polar you can see as well, minus 127, and CHF3 minus 78. So explain the differences in boiling point. What you would have to say is, first work out the intermolecular forces present. So if it's non-polar, what have we got here in methane? You can just say TD for temporary dipole, or PD for permanent dipole, or TD plus, actually I'm getting myself muddled up, PD. What would I have in methane? Which type? The temporary, right. And look at the mass, because I've only have temporary in that one as well. Look at the masses. Which molecule is bigger, CH4 or CF4? CF4. And because it's a bigger mass with more electrons, I'm going to have a higher boiling point. Because remember, although this number looks smaller, there's a negative in front. So I've actually increased in boiling point. Now I get to this one. Okay, the mass of this molecule is less than that, but more than that. So it sort of sits in between. But what intermolecular forces have I got for CH3F? Not all 3. I don't have all 3 because the hydrogen here is bonded to the carbon. I'm glad you said that, Andrew. That's why I asked it like that. Because a lot of students think, oh, as long as it's got hydrogen and fluorine or hydrogen and oxygen, it's fine. It's going to have hydrogen bonding. The hydrogen has to be covalently bonded to a fluorine, oxygen or nitrogen before any hydrogen bonding can take place. Now here these hydrogens are covalently bonded to the carbon. And because they're covalently bonded to the carbon, they can't hydrogen bond, because carbon is not stripping them of their bonding electrons, and it's not bonded to the fluorine. So I know that was a trick question, but I'm glad you said it, because hopefully everybody... Yep, so it's just the temporary dipole force of attraction and the permanent dipole force of attraction. So then, as I say, first you identify the types of intermolecular forces, and you think of all 3, and you think which one of those 3, is it one of the 3, 2 of the 3, or all 3? And then you have to talk about the strength. So here it was heavier molecule, and so stronger strength. Here it's not as heavy as that, so the temporary dipole will be stronger than methane and less than CH4, but it's also got the permanent dipole force of attraction because that molecule is a molecular dipole. And then, as I say, we've done the comparison. And so this is how you would write it out. So if you're watching the recording, you can pause it here and look at it in detail. Notice I'm talking about separating the molecule. You have to spell it out. So first spell out the types of intermolecular forces, then compare, and then talk about strength and energy needed to break those attractions, because you're separating it. Okay, and then that's the next comparison with the CH3F. Okay, I'll carry on because I have actually explained all that. Right, this is now from last year's exam. So you've got ammonia, fluorine, and hydrogen chloride, and you're first told to work out the attractive forces, and then you had to discuss the differences in the boiling points. Okay, so ammonia is temporary, permanent, and hydrogen bonding. Then remember, it's hydrogen bonding because the H is bonded covalently to the nitrogen, so it can now hydrogen bond with another ammonia. Fluorine, non-polar, so it only has the one type. That will not have hydrogen bonding, but it'll have the other two types. And then the same thing, you've got to compare all those different points. You can look at the answers on the internet, but that's just the way you would break it down. Remember, spell out the things. Don't just assume the teacher thinks you know it. You have to spell it out. Here's another one from the 2013 exam. You can see it's a pretty common question. And so you have to spell it out. Now, hydrazine, remember, if you're not sure what it looks like, draw the Lewis structure, and there it is. So it's actually not symmetrical, because although it looks symmetrical if I cut it down here, it's not symmetrical if I cut it across the bonds there. This side is not the same as this bottom bit over here. Will hydrazine have hydrogen bonding? Yes, because we have got a hydrogen covalently bonded to a nitrogen. Okay, so we first work out which ones are polar and which ones are non-polar, which ones can have hydrogen bonding, and then you discuss. So you look at mass, size, shape, all those sort of things. Right, so solubility. Solubility uses the same sort of thing because we're looking at the intermolecular forces of attraction. So what I've tried to show here are some water molecules, and I've got a polar molecule in here. So it can form temporary and permanent force of attraction. Water, of course, can form those two plus hydrogen. Now, when we trying to dissolve something, we have to break the intermolecular forces between the solute. So, can you see the orange attractions? So we need energy to break those, and we need to break the force of attraction between the solvent. So that's two lots of breaking we have to do between the solute and between the solvent particles. Where is that energy going to come from to break that? From heating, and that's why things dissolve quicker when you heat something. But it also needs to come from as attractions are formed. True, when there are collisions, you form an attraction, and that attraction does what? Release energy, or does it also need energy when an attraction is formed? So if you think of like if you're holding two magnets, do you need to push them together if they, correctly orientated? No, because there's that attraction, so it releases energy itself. You don't have to expend energy to push two magnets, a north and a south pole, together. So that those two types of energy must be more or less balanced. We need more energy or similar amounts of energy released when attractions are being formed. So these are the ones between the water and the solute. I hope you can you see the yellow? Yeah, okay. So that energy being released must be sufficient to overcome this barrier of breaking the orange ones and the green ones. So it goes step by step. It doesn't do it all at once. But in this area, as that bond gets formed, it releases energy which can break this bond, and which can perhaps, as they move around, you know, the green and the brown will start breaking and more yellow ones will form. And if that happens, the substance dissolves. Yes, it's additive. If however this attraction between the water and the solute isn't very strong, it's not going to break those hydrogen bonds. Will my substance dissolve? No. Okay. And hydrogen bonds are quite potent. So even polar molecules don't necessarily dissolve in water, because it's not forming a hydrogen bond here, it's just forming a permanent dipole attraction, and that may not be enough to break a hydrogen bond. The energy may not be sufficient. So as I said here, a substance will only dissolve when the energy released from the attractions is similar or more than the energy required to break the ones between the solute and between the solvent particles. Notice how I wrote it. I didn't say to break the intermolecular forces between the solute and solvent, because I'm saying between the solute and solute and between the solvent and solvent. Those two, you know, the orange and the green. So if I look at this now, here I've got ammonia dissolving, okay, in water. So if I have something that forms hydrogen bonds, I've made it both green. So if I now will form hydrogen bonds between the water and the ammonia, and that will be similar in energy or different. So in other words, are the yellow similar in energy to the green bonds? Again, no, they're all hydrogen bonds. So the yellow, because can you see, I've got this hydrogen covalently bonded to an oxygen, and it can form a hydrogen bond with a nitrogen of a different molecule. So that's a hydrogen bond. They're slightly different, of course, because nitrogen attracts less strongly than oxygen, but it's similar enough. And so ammonia is very soluble in water, because the solute-solvent attractions are similar in strength to the solute-solute and solvent-solvent attraction. Okay. So a substance that can form hydrogen bonds, also a substance that can form hydrogen bonds with water. That's what I was showing in the previous slide where I had formaldehyde. The formaldehyde can, although it can't form hydrogen bonds itself, the water can hydrogen bond with it. And as I say, a polar substance may be able to dissolve or may not. It depends. Okay, here's my formaldehyde. It can form or the water can form a hydrogen bond with it, even though it in itself can only form a permanent dipole force of attraction. And then solubility in a non-polar, it's really got to be only non-polar substances can dissolve, because the attraction between water and a non-polar substance is not going to release enough energy to break the hydrogen bonding, but a non-polar with a non-polar, it'll be similar. Okay. So, which one of these would be soluble in water? So spot which ones have got hydrogen bonding. Does this ethanoic acid have hydrogen bonding? Yes. So it will dissolve. This one is now a little bit tricky. Does it have hydrogen bonding? Okay, I know you're busy typing, so okay, yes, it'll form hydrogen bonding, but I've got an enormous non-polar end, so it's not going to dissolve very easily at all. So this actually would be insoluble in water. It'll float, on top of water. So it'll be like that oil floating on top of water. Methane. Will methane dissolve in water? No, because it's nonpolar. The attractions between this nonpolar molecule water is not enough to break the hydrogen bonds in water. What about this ester? It's actually ethyl propanoate. It's got oxygen, so it can't form hydrogen bonds in itself. It's got the oxygens, so water could form hydrogen bonds with it, but it's one of these in-between ones. It actually floats on top of water too, with only a little bit dissolving, so it's very, very slightly soluble, and it's because I've got fairly big chunks of non-polar parts to it. So it's now just the shape and size of the molecule is going to, although water can form hydrogen bonds with it, it's not going to dissolve very readily. So it's one of the in-between. But here's one where it's nice and small, very little non-polar part, so that'll dissolve. Methanol, dissolves very easily. So if we go through it, that is the answer. Right. Now, it is sort of past, but you started late. Do you want to carry on with entropy? Okay, we'll if that's okay with you. It shouldn't take us too long. So entropy, first of all, what is entropy and why is it important? It's a measure of the dispersal of energy. So we've been talking about energy all the time, the energy needed to break the bonds, energy released making bonds. Now, what happens to that energy is what the entropy is about, how it's dispersed. So it's related to particles, so in terms of the dispersal, as well as to the amount of energy. So if, for instance, I heat water up to start boiling, will my gas, my water vapor, have more entropy than my water? Yes. The reason being is, first of all, those particles are more separated. They're totally separated in a gas compared to in a liquid where they've still got quite a few attractions. So we've got lots of separate particles. Each little separate particle is carrying the energy away, okay? So it's being dispersed more. And also, in a gas, they are moving faster. And if they're moving faster, they're zooming around all over the place. And so there's more energy involved with that. So the entropy is how it's dispersed. How is that energy dispersed? It's given a symbol S, and notice it's uppercase, because you'll see it's often put in brackets, and you want to distinguish it from a lowercase s, which means solid. So the more particles in the system, the more the energy can be dispersed. The more energy the particles have, the more the energy can be dispersed. So it's like if you've got 10 buses, each person is a particle containing energy. If you've got a bus full of people, and that moves out, that's carrying out like a chunk of energy. So, but if you also have lots of little people singly moving around, both ways can disperse the energy effectively. Right, and then as I said, gaseous particles have more entropy than particles in the liquid state, and they have more energy than the ones in the solid state, because there's more energy moving around in a gas compared to a liquid compared to a solid. And so the easiest way to visualize entropy is disorder. So you might often be told, it's like a pack of cards, it gets disordered very easily, or a messy teenager's room. But basically entropy is basically it's the dispersal of energy, but if you think of it in terms of disorder, think of all the particles whizzing around in a gas. There's more disorder there than if they were all tightly packed in rows like an ice. So that's a good visualization in terms of disorder. So here, lots of order in a solid, less order in a liquid. You can see they've still got lots of attractions. They're moving around though more freely compared to a gas where they're moving around lots, going faster as well. And so there's a lot more disorder over there. Okay, so what we're going to look at here is if entropy is increased or decreased. Now I've said state whether the entropy change is positive or negative. So if entropy is increased, it's a positive change. If entropy has decreased, it's a negative change. So look at the number of particles. Right, it's negative over here because it's decreased. I've gone from 2 particles to 1 particle. So there's fewer particles, so there's more order in the system. It's like having just a few pieces of paper in your room lying on the floor compared to a whole pile of papers lying on your room on the floor. The room is messier with a whole pile of paper. So this one is delta S is negative. There's decreased and it's decreased because delta S is negative. The next one is positive, it's increased. Now there's 2 reasons for this. The one reason is I've gone from 1 particle to 2, but there's also another reason why I've got an increase in entropy. Now look at the states. I formed a gas. So I've gone from a solid and I've formed a gas. And remember, a gas is always has got more entropy than a solid because those particles are zooming around, they're not ordered. Okay, here it's decreased. Delta S is negative. Now have a look here. I've gone from 3 particles to 2. So that's one reason. So you have to spell out all the reasons. But there's also another reason why I've got a decrease in entropy. It's gone from gases to liquid. Okay. Now this one you should be able to work out. If I go from a solid to a liquid, what is happening to my entropy? It's increased. That is a mistake. Okay, mistake. It's the other way around. And hopefully I got it right here. Solid to an aqueous. Now, I haven't really done aqueous before, but can you see if I've got my sodium chloride, for instance, all packed nicely in a solid? In a solution, are those particles nicely ordered? Do I have more particles, less particles? Okay, they're not nicely ordered, correct, and I'll have more particles. So that's why there's an increase in entropy. Now, what you have to also talk about with entropy is, first of all, recognize how entropy has changed, but you also needed to work out whether a reaction is going to work or not, or strictly speaking, to be spontaneous. In chemistry, there are 2 parts to work out whether a reaction will actually work. The one is thermodynamics, which is what we're doing now, and the other part is kinetics, which is rate of reaction. And sometimes a reaction looks as though it could work. So according on paper, any diamond ring or diamonds you might have should all form carbon over time, but they don't because the energy requirements are too high. So I'm saying a spontaneous reaction doesn't mean it's going to just happen. Okay, it'll just ignite or something. It just means on paper it should work. Now, for a reaction to be spontaneous, the delta S for the system and the surroundings must be positive. This comes from the second law of thermodynamics, where it's pretty much says everything goes towards chaos. I don't know if you've heard of the second law of thermodynamics, but everything has to trend towards chaos for something to work. Nothing becomes more ordered. It has to become more chaotic. But it's got to be chaotic overall. So the system and the surroundings. My system is my coffee cooling down. Surroundings is the air around it. Okay? So coffee cooling. What's happening to those particles inside there? is the entropy getting increasing or decreasing in my coffee particles? The particles are slowing down, so the entropy is decreasing. It's negative because it's getting more order as they're slowing down, so the energy dispersal isn't that much. Okay, so you say, well, you know coffee cools. If you've got a hot drink, you know it cools down. So you know it's a spontaneous reaction. But we've just said that the delta S must be positive, and that's because of the surroundings. What's happening is that my energy from a high temperature in the hot coffee is being dispersed as heat energy to the surroundings. So what is happening to the molecules in the air? They're speeding up and they're moving around and it's becoming more chaotic. So the entropy is increasing in the surroundings and decreasing in the system. But overall, you know, there's overall the change in the surroundings is bigger because you know that your coffee will cool down. Okay, so the entropy of the surroundings is increasing, entropy of the system is decreasing, but overall that's bigger, so overall I have a positive entropy change, so your coffee will cool down. Now these are from past papers. This is from last year's exam. You've got an endothermic reaction, which I must admit is happening in the next lesson, so we'll ignore that bit. But outline the 4 statements about the changes in entropy. Now, if I have ammonium nitrate, I will tell you it cools down. So if I dissolve it in water, the reaction gets colder and colder and colder. What can you tell me about the entropy of the system? What is happening inside that test tube? Is the entropy decreasing or increasing? Now, it's a bit of a trick question the way I've worded it. So it's getting colder and colder, so you'd think the entropy is decreasing, but it's not like a cup of coffee. I'm dissolving something. So oh, okay, they made it actually just dissociating, so they've just broken it down. This will cool down, but I'm forming a gas. So is my entropy increasing based on this reaction? Yes. Sorry, I was thinking of another case where later on where I've made it dissolve. Yep, so I'm going to get an increase of the entropy, but what will happen to my surroundings? So I've done the system. What will happen to the surroundings? I've got 2 choices. We know it's getting colder. So what will the air molecules do because of this thing getting colder and colder? Will they speed up or slow down? They become more ordered. So it's going to be the entropy of the surroundings decreases. They're cooling down, they're becoming more ordered, so the entropy decreases. And that's the end. So any questions? No. Okay, so we'll stop there and we'll have another lesson next term. So all the best for the holidays. You've still got university leave, so university, so